Welcome to section 1.4.4, where we're going to learn how to graph a quadric surface given its equation. We're going to start with the sphere, and so the sphere of radius r centered at the origin has equation x squared plus y squared plus z squared is equal to r squared. Let's just take a second and look at where that comes from. If we imagine a point x, y, and z on the surface of the sphere, well, the distance from that point to the origin, all of the points are equidistant, so that's a distance of r. And so the distance from a point x, y, and z to the origin, any point x, y, and z on the surface of the sphere is going to be, well, you apply the distance formula, so the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. That distance must be equal to r, and if you square both sides and simplify, you get the equation of a sphere. Other quadratics are a little bit more involved, other quadric surfaces, I should say. And so we're going to first learn about a tool that will help us identify and sketch these quadric surfaces. And so we're going to look here at the curves of intersection with a plane that is parallel to one of the coordinate planes, like what we have in the diagram on the right is parallel to the xy plane. We can have planes parallel to the yz plane and planes parallel to the xz plane. If we look at cross sections or intersections of these planes with any surface, these curves that result in the cross section are called traces. In the planes, well, if the plane is parallel to the yz plane, it's a plane whose equation is x equals k. Similarly, parallel to the xz plane is a plane y equals k, and parallel to the xy plane is a plane z equals k. For example, on the right, the trace in the plane, well, that is the xy plane, so that is the plane z equals 0 of the cone on the right appears to be a circle. So analyzing the traces of quadric surfaces in these three types of planes, x equals k, so parallel to yz, y equals k, parallel to xz, and z equals k, parallel to xy, for different values of k is a very helpful tool in graphing these objects. Let's go, and before we start example 1.4.2, which we'll do in the next video, let's go and look at an animation of a quadric surface being intersected by these different planes and the traces that result. So here we have a hyperbolic paraboloid, right? Our quadric surface that looks like a saddle. And if we remember from a previous video, the curves that can be found on the hyperbolic paraboloid are hyperbolas and parabolas. And we can see that looking at cross sections of this hyperbolic paraboloid in the planes z equals k, x equals k, and y equals k. So the plane z equals k, right, we've actually got k here as minus 3.9, so z equals minus 3.9. That's a plane that is parallel to the xy plane. And if we change the value of k by sliding this up, so we can see those planes moving different k values, and we see the traces of the intersection of this plane with the hyperbolic paraboloid is giving me hyperbolas. If we slide that along, we can see the different values of k giving different traces, but they are all hyperbolas, including right there in the center. We've seen that before in the case of a double cone, where you actually end up by getting two straight lines. It's a I can't struggle with that word last time too, degenerate hyperbola. You can see before the hyperbolas switch from opening in the x direction to opening in the y direction, they pass through right at the origin right at the origin there, they are passing through two straight lines. That's the plane where z is equal to 0. If we switch to planes that are parallel to the yz plane, so planes in x equals k, planes in x equals k, and we take a look at the same thing for different values of k, here we can see the trace or the intersection, the curve of intersection with this plane of the hyperbolic paraboloid with these planes. These are giving us parabolas. So parabolas, downward facing parabolas in the planes x equals k, and in the planes y equals k, so we see the planes are now parallel to the xz plane. We're looking at the traces, in other words, the curves of intersection of these planes with the hyperbolic paraboloid, and we see that we are getting parabolas again, this time upwards facing parabolas. So this is the idea behind taking intersections, the curves of intersection. Now we are going to do this algebraically in the next example, but the information that results will be the same type of information, the same, give us what the curves of intersection or the traces will be, and that will actually help us sketch the graphs of the unknown quadric surface given its equation.